Now, since U, the molecular potential energy is independent of theta and phi would be the angle that your molecule forms with the z-axis. Your rotational energy is essentially that of a particle in a sphere. Okay? And so you can use the rigid rotor approximation for the rotational energy. So rotational energy is just B times J plus 1, where your restrictions for J are 0, 1, 2, 3, and so on and so forth. What is B here? It's your rotational constant. That's just h bar squared over 2I. I being the moment of inertia, which is mu r squared. Okay. 2 mu r squared. And mu is the reduced mass. Okay. And r is just the distance between the two. But what you actually have here is a vibrating rotor. So what you really have here is just the average r. Okay. It's an approximation. So this is just an approximate formula. And one thing we also mentioned when we did this in the lab, when we talked about this in the lab, is that because of anharmonicity, at high J levels, that average R actually stretches out because of what we call centrifugal distortion. So your formula is not going to be just the rigid rotor formula. You have to introduce correction terms to it. So it's just, what did we have in the lab? Bj, J plus 1 minus a centrifugal correction term. This D sub E is not the same thing as the D sub E we had earlier. That one's dissociation energy. This one is a centrifugal distortion constant times J plus 1 squared.